Okay, so our next property is onto. And we say that a function is onto if every element of the second set, t, is actually mapped to by some element in the first set. So what we have is something like this. Here's s, and here's t. And let's say that these points are here in t, okay? And what must be the case is that there's some point in s that maps to each of the points in t, okay? That's it. It could be that some points are mapped to more than once, for example, okay? You know, that's okay. There just needs to be at least one that actually points to it, all right? And with that intuition, how do we actually turn that into math? And here's a definition. So for each point in t, there exists a point in s, so that if t really is in t, then f of s is equal to t, and of course s belongs to s. Now I should point out that it's more natural to take this quantifier and stick it right in there. So for all t that's in the set capital T, there exists an s, which is in the set capital S, such that, okay? But I went ahead and put it here simply because I'm migrating the quantifiers. That will make it easier to prove. It saves me one step. It's not that much easier. Okay. Another way of actually saying this is like this. We say that the set of all f of s such that s belongs to s is actually the set T. Okay. Now T is known as the codomain. Right? And this set here is actually what's known as the range, right? That's the set of all f of s, where s comes from the domain. So another way of characterizing what it means to be onto is simply to say that the codomain is the exact same thing as the range. Okay, so that's what we have. Let's look at some examples. So for example, f of x is equal to 2x. If you're going from the rationals to the rationals, then this is an onto function. And this is why. If you simply let x naught be equal to y naught over 2, then in fact f of y naught over 2 will be equal to y naught, right? So for any y naught in Q, we can actually find an x naught that maps to it. Okay, so yeah, that's onto. Okay. Now let's try f of x equals 2x, the same rule, but this time over the integers. And over the integers is actually not onto, because think of 3. There is no integer such that 2x is equal to 3, right? So that one doesn't work. Okay. Notice it looks like the same rule, but like I said, they're different functions because they have different domain, different codomain, and that means that they have different rules, right? Or rather different properties. In this case, the property onto is true of the first one over the rationals, but it's not true of the second one, which is over the integers. Okay. Okay, now I know that we said that this is not a function, and it's not a function, but let's just imagine that students have only one major, right? So the function that maps students to departments according to the major would be onto, because we wouldn't want to have a department that doesn't have any majors, right? So you could actually look at it that way, right? And that's kind of a non-mathematical example of ontoness. And let's take English words and map those to positive numbers, positive integers. And the mapping is going to be the length, right? That is not onto, because there is no word in the English language that has, 19.5 trillion letters. Thank God, right? So no, that is actually not an onto mapping. However, if you think of the strings that are made up from letters A through Z, then actually length is an onto function. Because, for example, let's pick, 19.5 trillion. Then the string A, and then almost 19.5 trillion A's, followed by an A, actually has just precisely that length. So it doesn't matter what number you pick. I can always kind of find a string of A's that has that exact length. So that would be an onto function. Again, notice how important it is when we're talking about properties of functions that we know what is the domain, what is the codomain. Okay, so let's try to prove something. So f of x equals 2x from rationals to the rationals. We want that to be onto. So how will we do that? Okay. Well, to show that something is onto, then we need to prove the formal statement that says that for all y, I can find an x such that if y is a rational number, then x is also rational, and f of x is equal to y. You can actually almost ignore these parts, right? And just say for all y, there exists an x such that y is equal to f of x, and that's if the domain of discourse is chosen properly. Okay. Anyway, what are we going to do? We're going to take for all y, for all x, we're going to start removing the quantifier so we can get rid of the first one and that leaves us with just their existent x. So y belongs to q, x has to belong to q, f of x has to be equal to y, right? That's what we need to prove. So at this point, what we need to do is to choose the right value of x, or a right value of x, I should say. So how are we going to do that? Well, that's actually hard to do if we don't know what x is, right? So it makes sense to open up the definition of x to give us some sort of an idea. So here it is. Instead of f of x equals y, what we have is 2x equals y, right? And that's much more useful because now it's 2x equals y. So now I can choose x is equal to y over 2, right? Now I know how to make that choice, right? So now I can remove the quantifier, and I have y belongs to q. That should imply that y over 2 belongs to q, and 2 times y over 2 is equal to y, okay? But why does that follow? Well, that's all just properties of the rationals, right? So, for instance, if y is a rational, so is y divided by 2, right? If y is a rational, y divided by 2 times 2 is actually the same as y, because that's just y times 2 over 2, or y. So we're done, right? So that's how we can prove that a particular function is onto. Pick an element in the codomain, and then show that some element of the domain must map to the codomain. Okay, now let's look at f of x equals 2x, our same example, but this time over the natural numbers. To show that it is not onto, then what I need to do is show that the onto property is not true, right? So it's not onto. I'll take the quantifiers and I'll migrate them over to negation. So notice they split. There exists a y such that for all x, right? So I have now a negation over an implication. So we're going to push the negation into the implication, and this is kind of what it looks like, okay? I want to make sure that you're absolutely solid on how to do that, all right? Now, I'm going to show you just briefly how I might do that. So we have, it is not true that P implies Q and R, okay? Okay? And so this is the same as saying it is not P or Q and R, right? Because that is implication. And then I'll distribute the not, so I have not P and not Q and R, and that follows from De Morgan's, right? And this is just P and not Q or not R, and again this is De Morgan, right? So this is actually what the negation of an implication is, okay? So basically, if you have not hypothesis implies conclusion, that is the exact same thing as saying the hypothesis is true and the conclusion is not, okay? That's how you negate implications. And in this case, since our conclusion was an and, then we can actually distribute the not inside to get not Q or not something, okay? So that's how we got to this point here. Okay, all right. So now to continue. Okay, we want to get rid of the there exists a y, and that means that we got to make a choice. So what y is it that can't be represented as 2 times an integer? Well, any odd y will do. So we're going to choose 3. Okay, so there's our choice, and now we'll get rid of the for all x, and to do that we leave this unknown constant, right? But now what we can say is that, well, 3 belongs to n. That's just true, right? You know, so that's not a problem. But this part is a problem, right? So f of x cannot be equal to 3 for any x that is a natural number. Okay. Now this looks a little kind of ugly, right? But it's actually an implication, right? That's because it's not something or something else. So let's see that. Right, so we can actually write it in this form, right? And now it's obvious that that's true, right? If x is a natural number, then f of x, which is 2x, can't possibly be true. Now, to kind of make this super deep formal, right? Then I'll go ahead and expand f of x, make it 2x not equal to 3. And this is just true by properties of the naturals. Actually, it's the quotient remainder theorem again, okay? And that's because I know that 3 is equal to 2 times 1 plus 1, okay? And by the quotient remainder theorem, then that tells me that that's my quotient, that's my remainder, and that those are unique. Okay, so in particular, 2x cannot be equal to 3 because 2x plus 1 for a specific x is equal to 3, and like I said, that choice of quotient and remainder are unique, so that can't be. So that's the argument that shows why this function is an onto, right? All we have to do is find one element that is not mapped. I should say one element in the codomain that is not mapped by anything in the domain.